Okay, here we are.
Okay, good afternoon, everybody, or good morning, good evening. I don't know where you are, where you all are. This is the last PLUMED Masterclass for this first series. And we have seen many things in these lectures, how to analyze simulation with PLUMED, how to perform enhanced sampling, free energy calculation with metadynamics, umbrella sampling, replica exchange methods, how to use complex collective variable with Garrett, to do statistical analysis, and all these kind of things. And today we will talk about how to do all these things faster and how to optimize the performances of PLUMED enhanced simulations. Before starting the few introductory slides, I want just to remind you that in 2 weeks, we will have a poster session for all the participants of the masterclass. So I invite you to fill in the form in which you state if you're interested to participate, if you're interested to bring a virtual poster and a title for this poster. And the link to fill this form, you can find it in the on Slack under the channel announcements. So I invite you, all of you, to fill in the form as soon as possible, so we can better understand how to organize this virtual poster session. Okay. So at this point, probably I don't need to repeat this slide about PLUMED. You know very well that it's a community effort, and with some core developers, including me and Giovanni, that we are here today. And it's about enhanced sampling methods, free energy calculation, and analysis of MD data. And we spend a couple of slides showing a bit the structure of the code and how it interacts with the main molecular dynamic engine. So we have seen that you can use PLUMED to analyze standalone utilities to analyze trajectory, but in most of the lecture, probably we have used PLUMED in combination with a molecular dynamics code. And so I will give you a sketch about how PLUMED interact with the MD code. And there are different points in which there is communication between the MD code and our library. The first one is in the initialization of the code, in which some parameters are read from a PLUMED input file. Some others are communicated from an MD code, for example, the temperature of the system. And this is done once at the beginning of a simulation. And then there is a communication between the MD code and PLUMED at each molecular dynamic step. So each time, each integration, let's say, of the Newton's equation of motion, there is a communication of the position of the atoms from the MD code to PLUMED, and the position of the atoms are used to evaluate these collective variables that we have seen in previous lectures, and also to calculate the derivatives of the collective variable and of the force and of the potential that you are adding to accelerate the dynamics, for example, with respect to the atom position. Once you have this correction to the force field of a MD code, sometimes using history-dependent schemes like metadynamics. These corrected forces are communicated back to the MD code that can add let's say, the force field, normal forces of MD, and then evolve the system and the next step. And so a little bit of a general overview of the general structure of PLUMED. So the software in this version 2 of PLUMED is built around a core of functionalities and methods, and it's let's say, divided in different areas of modules. I will show in the next slide. And of course, it must interact, so it has a window toward an interface toward different molecular dynamics code. And we provided this interface for several different codes. Sometimes you need an external modification of the codes, which we call a patch, that you can find in our library. And for example, for Gromax, DAMD, and other codes, you have to modify the code to enable PLUMED functionalities. For many other codes, this patch PLUMED patch is natively implemented in the source code. So you don't need to do basically anything to the source code. For example, CP2K, Number, or LAMPS OpenMM natively support the use of PLUMED. So PLUMED is a standalone, it's a library, and it's interfaced with this MD code, and sometimes you need to modify the code to enable using this library. On the other side, inside PLUMED, each functionality, each action, which is what we call like the distance between two atoms, or an harmonic restraint, or the print command, is coded as a C++ class. And if you go inside the code and you want to look at this C++ file, you will see that each file contains the implementation of what you're doing, for example, the distance CV, and a documentation in the same file, so you can have a look. And this is used to build automatically our manual. And this action use some tools, basic tools that are available in the PLUMED core. For example, if you use metadynamics with grids, these grids are functionality that are shared throughout the code, and you can reuse it. Or if you want to use periodic boundary conditions, these are a general tool that you can reuse if you want to implement a new collective variable. In the spirit of C++, which is very modular, you can reuse other classes. So the code itself is subdivided in a core of functionalities and in different, let's say, modules or group of actions. One are the callvar, let's say, the collective variable, like distance, angles, and a long list of collective variables to study different kind of problems. Then we have a collection, let's say, of action, which we call bias. So we have the method to add something to the energy, to the force field of molecular dynamics. For example, an harmonic restraint, which we call a restraint, a metadynamics bias potential, which is history dependent, and many others. And then we have separate modules, sometimes contributed by other people, that can be, let's say, enable or disable during the compilation of the code, which provide other functionalities. For example, a class of collective variables that are useful to study certain types of problem in material science, or in chemistry, or in biology. So we have different modules which are independent of PLUMED, but are provided in the PLUMED distribution. And they can be licensed to different authors of the code. Okay, so today we talk about performances, and it's useful to understand when this is a problem to make your code faster. There are certain cases in which the calculation of a collective variable might take a significant computational time, because certain collective variables by nature are expensive to calculate. Sorry. Because they involve a large number of atoms and complicate formulas, and so it takes a significant amount of time to evaluate. Some of these, here is an example of some of these collective variables. For example, to standard order parameters, to study some order around atoms, which are very useful in material science, I think. Giovanni, you can correct me if I say stupid things. And then there are path collective variables to study conformational changes between different, for example, a state A and state B. And this is often expressed in terms of a path, and so different reference conformation. And these conformation are represented by, can be represented by many atoms, so they are computationally heavy to calculate. Typically, the collective variable that quantify the amount of certain secondary structure type, like alpha helix or beta sheet, are kind of computationally expensive to calculate. Low dimensional representation like sketch maps or others that Garrett explained to you are most of the time expensive to calculate. Energy like the BioUCL or experimental collective variable. Let's say if you want to simulate and restrain a cryo-electron microscopy map, you have to use a large amount of a large number of atoms, and it's complicated to calculate. So the total amount of time that the code spent inside PLUMED becomes significant with respect to the amount of time needed by the calculation of a force field. So if you want to estimate how much time is spent inside Plume doing Plume related stuff, you can look at the end of the log file, and you will find this list of let's say of measurements, in which there is a total amount of time spent inside Plume in the first line here. So here at the end, you will see, apart from this is specifically for GROMACS, this first part, and you will see already the performance of GROMACS in nanosecond per day in combination with Plume. So this already gives you an idea of how fast is your simulation. And other codes might have a similar thing that tells you at the end of their log file how much fast is the code. So you can compare with and without Plume. And when you have Plume enabled, you have an additional panel at the end that tells you exactly how much time is spent inside Plume for doing different things. And one of the most important things is the calculation, so what we call forward loop, so the calculation of all the collective variable and the restraint. And this is here at point number 4. And the second point is, once these are calculated, you have to apply all these, to apply the correct forces coming for Plume, so the correction, and this is a cost that is typically scales like the number of atoms involved. The collective variable might be extremely computationally expensive and scale, for example, quadratically with the number of atoms involved in the definition of a CV. Usually the backward loop, which is the propagation, should scale with linearly with the number of atoms, but still might be expensive. And finally, certain variable needs an update. For example, metadynamics is time dependent, so it needs to do from time to time an update operation. And this is also, you can find it here in this summary of the timings inside Plume. So this is the first thing that you can do to measure performances. If you want to go into the detail of the individual collective variable that contribute to the timings, you can add on the Plume input file this flag, debug, and detail timers. If you add this to your input, you will have basically the same information, but you will have a breakdown in terms of each collective variable that you are defining, each action that you have defined here. So here, for example, you can see the forward loop, which is a calculation of variables, is breakdown in every single line that you have in your Plume input file. So here you have 2 collective variables and other action with no name. So there is a number, sorry, in Plume when you didn't name that particular action, and you can look at how much time each call here, each call to this action will take. Of course, there are fluctuations. This is just an average, but you will have also a minimum and maximum value that this particular line of in Plume will take. And then you have a total overall, let's say, the cost to this particular action. For example, here you are calculating this collective variable, I think 1,000 times, and this is the total amount of time spent in the calculation of this variable. So in this way, it's very easy, if you observe a slowing down of your simulation when you're using Plume, it's very easy to pinpoint the location in Plume that is the cause of this slowing down. So it's a good way to, let's say, debug problems or particularly intense parts of your calculation. It takes some time to let's say, prepare and accumulate the data for this table. So if you need really for production, this is better to switch it off. But in the beginning, if you want to understand what Plume is doing and how much time it takes, you can activate this particular line and you will have all this information. So the thing that Plume does, there are certain things that you can do to make Plume run faster. The first thing actually is not done by Plume, but it's done by the molecular dynamics code that is working alongside Plume. For example, GROMACS does these things that I will tell you. In many cases, the molecular dynamics code runs on a combination of GPU and CPU. And so there is part of the computation that are done on the CPU and part of the computation that are done on the GPU. PLUMED in 99.9% of the cases runs only on the CPU. We will see a few exceptions later, but it's run only on the CPU. And it runs on the CPU while the MD code is doing its task on the GPU in parallel, as you can see in this graph. If the calculation in the PLUMED calculation is too expensive, then the molecular dynamics code, like Romans, shift some part of the things that he has to do to the GPU. So this is what is called a load balancing. So since the part of the CPU is taking too much time, the code automatically put additional work and load on the GPU. In this way, the overall amount of time spent in the calculation of the MD part of the PLUMED part is optimized. And usually this makes the PLUMED overhead, so the cost of using PLUMED, much smaller. So this is the first thing to optimize performances that is not actually done by you. The second thing that we did inside PLUMED is we parallelize some basic core action done in PLUMED and also some collective variable using basically two techniques. One is MPI parallelization, and the other is OpenMP parallelization. I don't know if you know the difference between these two. I don't want to go too much into the details, but both are used to, let's say, split a series of tasks to do. For example, sorry, the calculation of collective variables that requires sum in many distances. This summation can be split between different cores of the CPU, and then at the end, these cores need to communicate somehow and put together the result into your collective variable. So this is done in many CVs using these two different techniques. And some example, some of the collective variables are written here. For example, coordination is something that can be trivially parallelized because it's a sum over different pairs and distances between pair of atoms and calculation of certain switching function. This is it's a task that is easily can be divided between different CPU cores. To use these functionalities, you need to make sure that you have compiled PLUMED with MPI support. So you need an MPI compiler, and you can check if a PLUMED has been compiled with MPI. If you look at the log, once you configure PLUMED, it's very clearly stated that PLUMED will be compiled using MPI. If you don't believe this, you can have a look at the makefile.conf, and you will see here that is highlighted with PLUMED is using MPI. As far as the other parallelization method, which is OpenMP, you can check at runtime, PLUMED is producing a log file, and in the beginning of the log file, you will see how many threads, so how many CPU cores in parallel PLUMED is using. In this case, 20. This is set automatically when you use PLUMED with for example, Chromax, I think also other MD codes, to make sure that you're using the number of cores that you expect. For example, the number of cores that Chromax is using, you can really set the number of cores used by PLUMED by this, using this bash command, export PLUMED number of threads, and you can set, for example, to 20. But this, I repeat, when you use with Chromax, it should be done automatically, using the same number of cores that Chromax is using. And if you're using the driver, this must be set manually. So this is as far as parallelization is concerned. So there are some very, very, very few collective variables for which we are trying and experimenting an implementation of a GPU. This is done using different more user-friendly libraries, such as libtorch. If you're familiar with machine learning stuff, you're familiar with PyTorch, and libtorch basically is a C++ version of PyTorch. And you can see here, for example, what we want to calculate is these huge densities, three-dimensional densities that are typical of this cryo-electron microscopy experiment. I don't know if you're familiar with it, but it requires calculation of many atoms, in this case, like 12,000 atoms, and we need to calculate the kind of electrostatic density in the three-dimensional space, so in a grid which is typically of 40,000, 50,000 points. And to do this on the CPU, it requires a lot of time, but this is an operation that the CPU can done very well. So we decided we are trying to port this calculation only of the CV to the GPU using libtorch. And if you can look at the difference performances, so this is the timing, let's say, breakdown that I showed before, and this is just the calculation of a collective variable. You can gain a factor of 10 if you calculate this complicated density on the GPU. Okay, I think at this point I'll leave the presentation to Giovanni, who can continue talking about performances.
Thanks, Max. Can you see my screen? Can you see my presentation?
Yes.
Yeah.
Yes.
Okay, great. So I just have a few more slides on this. So yes, that was the next slide. So yeah, there's another trick that you can use to improve the performance of your calculation, that is multiple time stepping. It's very simple to use, and it's kind of general, so I want to give you an idea of how it works. So first of all, this is based on a formalism that was introduced in the 90s by Mark Tuckerman and by Sexton independently. And the original derivation is based on using Trotter splitting, and but actually the final rule of the thumb is pretty simple. So the idea is that you can take a term in your potential energy function that in this case is the contribution of Plume, let's say the metadynamics potential, and just apply the forces resulting from that every n steps, scaling them up by a factor n. So let's say you apply them every second step, but you apply twice the force. In this way, the total transfer momentum is the same. And you can see that if the factor n is not too large, you can get very good integration of the trajectory. And the nice thing of this approach is that it gives you a reversible integrator. And the one thing that you can do with PLUMED is that you can also check for energy conservation, but separately you can measure the, let's say, non-conservation of energy that is due to the PLUMED contribution. And that's useful because that means that you don't need even the MB engine to conserve energy, maybe because you're running in some ensemble where it's difficult to check energy conservation, but still you will be able to assess this from PLUMED. Let me just show you an example of this. So this is from a paper where we originally introduced this. It was for this the bi-UCL electrostatic interaction that we were computing between some RNA and the protein, so two very large groups. So this is a double sum, was pretty expensive. And then the idea is that if you compute this the bi-UCL interaction energy only every second step, you gain a significant performance. And then here, I don't know if you can see my pointer, you can see the free energy estimated with a short metadynamics. It's just to sample one minimum here. And you see that if you choose n equal to 1 or n equal to 2, you basically get the same result. And as you go up to n equal to 3, you start to see some significant discrepancy, and the minimum jumps to a different position. And here you see this effective energy conservation that you can monitor with this command. And you see that basically it's just fluctuating around constant in the first two cases. And then as you go to n equal to 3, there's a significant drift. So you can use this to check the accuracy of your result, let's say, without the need to perform a separate validation with a shorter value of, with a smaller value of n. So how to activate this? The idea is that PLUMED automatically computes variables only when they are needed. So if a variable is only printed, for instance, and not biased, let's say it's printed with a statement which is print stride equal to 100, then it's computed every 100 steps. But then typically when you add biases like meta-D or restraint or any other bias, typically those biases are acting at every single step. If you instead specify stride on the same line as a meta-D or restraint, then this will enable multiple time stepping. So you can just add stride equal to 2 on your meta-D line, and you will be able to enable this. Okay, this benchmark for this from this old paper. So the speed is actually what we could do in 2014, in this specific case, the speed up was really significant because the cost of and this is what you see plotted here is really the cost of that's the inverse on the performance. Let's say days per nanosecond, including the entire calculation. And clearly you cannot beat the GROMACS only speed, but as you increase n, you can approach that. And this is really useful because even a small factor like 2 is often correct and give you a significant speed up. Okay, that was just one of the tricks. We have one page in the manual that you can find. It's one tab called Performances, where we try to collect all the tricks that we know that can be used. So you can just go there and browse the manual to find ideas. Okay, so I think we are done with the lecture. Let's say now, as usual, we will quickly skim through the exercises to give you some guidance. So as usual, you will find in the masterclass tab of the plumed.org website, you will find all the links. So let me now maybe exit the presentation and I will go, I think you can still see my screen. So I will go to the website here and I will click here. Okay, let me maybe change a bit the font. Okay, fine. So, okay, there's something a bit different in this class with respect to the other ones. So the main difference is that the results will be significantly dependent on the hardware that you're using. So I think you should be able to run these exercises on a laptop, but I would highly recommend if you have access to run them on a workstation. And I think all the exercises can be done also with the older versions of PLUMED, I guess. So maybe if you have access to a cluster where you have PLUMED 2.6, maybe you can try as well and see if the performances are different. Okay, the material can be found on GitHub as usual, and here you have some recap about how to measure performance, but that was already explained by Max, so you have exactly the same examples here. So let me quickly go through the first exercise. That's dissociation of NaCl in water. This is a pretty simple problem. You will find the TPR file with the topology for a pair of ions in a box of water. And the goal here is to compute the free energy as a function of the distance between the two ions. And what you will have to do is to start with this input file. So let's quickly see this. Okay, maybe this, if you've never used it, I like this, to use groups made of 1 atoms just for the purpose of using names that I prefer, like Na and Cl instead of distance between atoms 1 and 2. And then here, what we are doing, we are computing D, which is the distance between the two atoms, and then the coordination number of okay, but too bad. This should have been Na with water, against water. That's actually an expensive variable. And then we are doing metadynamics on these two variables. So this is a 2-dimensional metadynamics. You can run it with this command. You can play with the number of steps and see what happens. So let's say you can do this in the order that you prefer, but I would suggest you to follow the list that is here. So first, optimize the calculation of the metadynamics bias. There is some suggestion here on how to do it. And this is basically an optimization that should not really change the result. Maybe it could change it a bit. So it's not strictly the same trajectory, but should more or less give the same efficiency in the algorithm. And so you can just monitor the speed in terms of nanosecond per day. And you can try to optimize the parameters here. And then as a second thing, you can say, try to make the calculation of the coordination number as quick as possible. And again, there is little guidance here, but try to browse the manual and find tricks to do it. You can then try to make GROMACS run as fast as possible. This could depend a lot on the hardware that you have. And another comment is that, so to make sure that everyone is able to run these exercises, we have these Conda packages available, but yeah, they are not really optimized for the hardware on which you are running. So if you want, you can just optimize the simulations by learning how to compile GROMACS and PLUMED by yourself on your machine. And finally, this final step is pretty different from the others. So far it was basically obtain the same or a very similar trajectory in a shorter time, but actually you can gain a lot by tuning the algorithm. So I would suggest also to play with the parameters of metadynamics to see if you can optimize them to be able to reconstruct the profile in a shorter time. And here there are some ideas, but you can clearly experiment with other things. And then next time we will compare our results in the next lecture. Okay, and finally, the last thing is to connect with something more physical. This is pretty simple, but I think it's nice if you think about it, if you've never did it. So try to think and how to compute the standard binding free energy for these two species, starting from the free energy profile that you have obtained in the previous points. Okay, good. So I'm done with this part, so we'll stop again, and so that Max can share his screen for commenting the second exercise.
Yes. Okay. The second exercise, if you participated to the metadynamics masterclass, you probably will recognize this example. It's a conformational change between an alpha helix and a beta sheet rich conformation of a C-terminal domain of this virulence factor. And we use this example to devise CVs for metadynamic, to carry out a metadynamic simulation to enhance the transition between these two states. Here we use the same example, but with a different, let's say, purpose. And the collective variable will be given in the GitHub of this exercise, and you will need to optimize it. But before going into the details of a collective variable that I've already prepared for you, I will tell you one thing about this system. So in the way we simulate this system is not in explicit solvent or atom, but it's using a simplified, it's called structure-based potential, called SMOG. So if you want more information, you have to click there. What you need to know is that this SMOG energy function is designed to have usually its global minima in one native structure. Here it's a bit more complicated because you have two, let's say, local free energy minima. So this energy function is designed to have two local minima that correspond exactly to this beta barrel and alpha helical state. One of the two states is more populated than the other, so it's the beta barrel state, the state B. So we focus just on this. And so this energy function is written, let's say, promotes these contacts that are formed in the native states in some way. So in this situation, a good collective variable to enhance sampling is something that is correlated with this energy function and with the energy of the system. And in this case, the number of native contacts in one of these two structures is usually a good collective variable for enhanced sampling. So what I've prepared in the GitHub repository is, apart from the GROMACS input file, the GROMACS topology file to run the simulation, and two PDB file just to have a look at the two structures, I prepare a PLUMED input file with a list, let's say, with a definition of the total number of contacts in the beta barrel state here. And this is a very complicated, I think it's almost 1,000 lines of PLUMED input file to count the number of native contacts of a certain conformation. And you can, if we quickly have a look at the PLUMED input file, you first, let's say, reconstruct the conformation which might be broken by periodic boundary condition. This is just to keep track during the simulation of how far you are from state A and state B. So it's just an RMSD which is used to monitor the your simulation, and you don't need to change or optimize this because it's a C alpha RMSD. And I think there's no need to optimize this unless you want to do it. And then we have to define the number of contacts. And to define the number of contacts, we need to first calculate the distance between certain atoms. And the atoms that we calculate the distance are those closer than 6 angstrom in the reference PDB file of state A, which is the beta barrel. So we will see a list of 379 distances in the PLUMED input file. At this point, once we have the distance, we have to define a contact. So it means we define a contact when the distance is lower than usually a certain threshold. And this is done in a continuous way by using a switching function that goes from 1 to 0 in a let's say, reasonable range of the distance, so around 6 angstrom. And to do this, we we implement the functional form of the switching function in the PLUMED input file using the custom action. So you will see for each distance, maybe I can make this bigger, if I can do it. For each distance, we define a custom CV, which has a functional form of 1 minus the error function of the distance to the 4th power. And so for each, this is the functional form, is the same for each contact. The only difference is the argument, which is one of these 379 distances. So this is one contact. And then what we need to do is to sum over these 379 contacts, native contact, to count how many of those are formed in a certain conformation. So you will have this, you will see this very, very long line, which correspond to these combined lines. So this is a very long PLUMED input file that does the trick of computing the number of native contacts, but it does this in a very inefficient way. So once you have defined the CV, you can use it for metadynamic simulation. So I've put here some of the parameters that you might want to optimize, as Giovanni asked you for the previous exercises, and then a usual print line for the value of a native contacts and the RMSD just to monitor the simulation. Okay, so what you need to do in this exercise is to optimize the distance-based CV that I wrote in the PLUMED input file in order to improve the performances. So you should monitor and report the speed up that you obtain with your optimized CV with respect to the one defined in the input file. To do this, you don't need to run to converge a free energy profile for the CV that I provided in the input file. You just run and measure the a little bit and measure the performance. The second task, once you have optimized the CV, you need to optimize the performance of the metadynamic simulation itself, as done in the previous exercises explained by Giovanni. So you optimize the calculation of the bias and metadynamics parameters. Number 3 is really to converge the simulation as explained in Masterclass 4 and calculate free energy and free energy to evaluate the stability of this beta barrel state, so free energy difference between the native state and other states, and with an error, hopefully with an error estimate, as explained in Masterclass 4. So I won't give many suggestions, just a few. The first one is you need to use the manual quite heavily to learn how to optimize this CV. There is one CV that might be useful, which is implemented in PLUMED, which is called coordination, and can be defined using a custom switching function. When I say optimize a CV, it means that we need a CV that is exactly the same as the one implemented here, not something that is kind of correlated to this, something that is exactly equivalent to the one defined here. So you might want to compare once you have the two, this one you have already, you have optimized your calculation, you want to compare that they actually give the same value for the number of native contacts. Okay, so you might want to look into the coordination CV. Finally, as Giovanni explained, you can use multiple test stepping to apply the metadynamic bias every 2 or 4 steps. You can play with this parameter and monitor the conservation of the plumed energy. So I think this is all for this exercise. I can probably stop sharing the screen. And I think at this point, if you have questions about the slides or the exercise, it's time to ask them. Any questions? No question at all.
No questions, so I will stop streaming now.